Hello, we're back with another lesson. This time it's continuity. So when you finish this section, you should be able to determine whether a function is continuous at a number, determine intervals on which a function is continuous, use properties of continuity, and use the intermediate value theorem, also known as the IVT. Okay, so sometimes the limit as x approaches c of f of x equals f of c, and sometimes it does not. In fact, f of c may not even be defined, and yet the limit as x approaches c of f of x may exist. So in this section, we're going to investigate that relationship between the limit as x approaches c of f of x and f of c. So let's look at this figure here with all these graphs, 5 graphs, and we're going to look at all the just the limits. If you look at the first graph, notice that if I want to find the limit as x approaches c from the left, it's equal to the same limit as x approaches c from the right, and it's also equal to f of c. Notice, so if we approach from the left, the graph is approaching that y value. If we approach from the right, the graph is approaching that same y value, and f of c is this y value here, so all three are the same. So that's a nice graph. That's what they call it, nice, in quotations. Okay, let's look at the next one. If I approach c from the left, it's approaching this y value. It's not equal to it, it's just approaching it. If I approach from the right, I'm approaching the same y value. So that tells me that the limit exists because the one-sided limits are equal to each other. But notice that f of c is not equal to the limit because f of c is this y value right here. It's not the same as that one there, but the limit exists. Let's look at the next one. Again, if I take the one-sided limits, if I approach c from the left, I am approaching that y value. If I approach c from the right, I'm also approaching the same y value. And since there is no y value at c, notice that there is no dot. There's an open circle there. F of c is not defined. Let's look at the next type. So once again, we're going to do one-sided limits. So as I approach c from the left, we are approaching this y value right here. And as I approach c from the right, we are approaching this other y value. Notice that the y values are not the same. Okay, so the limit does not exist. But f of c is defined. It's telling me that when x is equal to c, we have this y value there. So yes, the limit does not exist, but f of c is defined. Let's look at the last one. So this one, as we approach c from the left again, we are approaching this y value, whatever that may be. And as we approach c from the right, we are approaching this y value, whatever that may be. Notice that the y values are different. Therefore, the limit does not exist there. But also, f of c is not defined because at c, there is no y value. Of these 5 graphs, the nicest one is the first graph. In that graph, the limit as x approaches c of f of x exists, and it's also equal to f of c. So yes, the one-sided limits are the same. That tells me that the limit exists. Also, it's equal to f of c. So that means that it is continuous at that point. The other graphs are all discontinuous. Now, let's look at the definition of continuity. So the definition of continuity number says this, that a function f is continuous at a number c if the following 3 conditions are met. It has to be all 3 conditions. First one, f of c is defined. That is, c is in the domain of f. So yes, it's in the graph. There's no holes, there's no breaks, nothing. It is defined. The next one, the limit of as x approaches c of f of x exists, meaning the one-sided limits are equal to each other. So we can put one-sided limits are equal. And the last condition is that the limit as x approaches c of f of x is equal to f of c. It's equal to that y value. Now, before we look at our first example, I want you to look at this note. A polynomial function is continuous on its domain, meaning all real numbers. So if a function is a polynomial and you recognize that it's a polynomial, it's definitely continuous everywhere. So there's no need for you to check the 3 conditions. Also, a rational function is continuous on its domain. So what it's saying is that a rational function, since it's basically a fraction, if it's continuous on its domain, then it is continuous at that number too. So let's look at a graph. Here we have this function, f of x, x to the 4th minus 1 over 1 minus x, and they also gave us a graph. If you look at the graph and you try to draw it, you can't draw it without lifting your pencil, because here, when x is 1, I have to pick up my pencil, go to the other side, there's a hole. So at that x value, that is a point of discontinuity. So the point or points of discontinuity for this function is at x equal 1. Now, what condition is or are not satisfied? Well, the condition is that f of 1 does not exist. That would be, if I go back to the definition, it would be this one. F of c is not defined. That condition is not met. Okay, we're going to look at another graph. Now, this is a piecewise function. It's made up of 3 functions, but we're not looking at that. We're looking at the graph. So notice that here at this x value at 3, when x is 3, notice that we have an open circle, a hole. Even though there's an open circle, if you look at the limits, if we approach 3 from both the right and the left, it's approaching the same y value, so the limit exists. Also notice that f of 3 is equal to 9, so f of c is defined. So let's see, the point of discontinuity in this one would be at x equals 3, because that's where the hole is when x equals 3. Now, which condition is not met? The condition that is not met will be the last one, where the limit as x approaches c of f of x, that is not equal to f of c. That's different. Here, notice that the limit as x approaches 3 of f of x, that's equal to, I believe it looks like 5, but f of c, sorry, let me change it, f of 3 is 9. So f of 3 is 9. So notice that the limit is 5, but f of 3 is 9. They're not equal to each other, so therefore, that is the condition that is not met. Okay, so for this one, I want to look at 2 things. First thing is a function. This is a rational function. And what we need to do is look for the domain first. Now, to look at the domain, notice the denominator. We have x squared minus 4. And what we do not want in the denominator is a 0, because then it would be undefined. So here, x squared minus 4, I know that for the domain, x cannot equal a negative 2 or a positive 2. And the reason is because if you plug in a 2 here, you get 0 in the denominator. And if you plug a negative 2, you also get 0 in the denominator. So therefore, it would be undefined there, not defined. So that would be our domain. All real numbers, but x cannot equal negative 2 or 2. Now, if you remember from class, if the denominator is equal to 0, then that means you have vertical asymptotes. These asymptotes happen when the denominator is equal to 0. So at negative 2, there's supposed to be a vertical asymptote, and at positive 2, there's supposed to be a vertical asymptote. That's why the graphs seems like they jump after 2 and negative 2. So therefore, the points of discontinuity would be x equal negative 2, x equal 2. That would be the points of discontinuity. Now, which of the three conditions was not met, or met, sorry? Well, f of negative 2 is undefined, and f of 2 is undefined also. So one of the conditions is not met, and in order for it to be continuous at a number c, all three conditions have to be met. Okay, let's look at this last one. Now this last one, this one's going to be easy. This, if you recognize it, that is a polynomial. And earlier, I said that if a function is a polynomial, it is continuous everywhere. So let's just look at the graph anyway. If I would draw this graph, I would trace it. Notice that I'm not lifting my pencil anywhere. Also, if we look at this point, when we take the limit, it's the same y value. Also, at 1, it is defined. It's the exact same thing. So this one has no points of discontinuity. And let me go back to see what it said before. Conditions that are satisfied or not. Well, the conditions are all of them. We can say f of c is defined. The limit as x approaches c of f of x exists. And finally, the most important one, that the limit as x approaches c of f of x equals f of c. So for this one, all three conditions are met, and therefore it is continuous everywhere, and it has no points of discontinuity. Okay, so now we looked at graphs, so now we're going to look at these following problems where we're going to determine whether the function f is continuous at c. And this time we're going to do it algebraically, and we're going to be looking at the definition of continuity at a number. So the first thing that we should do is check the domain. So the domain for this function is all real numbers. And the reason is because this x cubed minus 5 is a polynomial. And the question was, is it continuous at c equals 5? And since it's a polynomial, it means that it is continuous everywhere. And that is according to the note that we had. This one right here. A polynomial function is continuous on its domain. Therefore, when I look at this function, f of x, x cubed minus 5, and it's being asked if it is continuous at c equals 5, we say yes. Yes, it is. Yes, it is continuous at c equals 5. And the reason is because it is a polynomial. And that is why it is continuous everywhere. And it has no points of... Okay, so it got cut off. I said that it has no points of discontinuity. Okay. Okay, on to number 3. So here we have a rational function, x over x minus 2. And whenever you have a rational function, you have to be careful. You want to check the domain of the rational function. In order for you to do that, let's check the denominator. So in the denominator, we have x minus 2. And what we want to do is find out when is it equal to 0. So set it equal to 0 and then solve for x. If we solve for x, we get x equals 2. So what that tells me is that when x equals 2, the denominator is equal to 0. Therefore, we cannot have a 2 in the denominator. So we say that the domain is all real numbers, but x cannot equal 2. That would be our domain. Here's the thing though. The question is asking us, is it continuous at c equals 2? Well, since x cannot equal 2, that means that 2 is not in the domain. The c, it's the same thing, is not in the domain, and therefore it doesn't satisfy one of the 3 conditions. So let me go back so you can see the conditions. Condition number 1, f of c is defined, c is 2. F of 2 is not defined, c, which is 2, is not in the domain. Here it says that it has to be in the domain, but it's not. So what that tells me is that this function is discontinuous at c equals 2, which is the same as x. So we can say discontinuous at c equals 2 because f of 2 is not defined. So therefore it is not continuous. So you can say either not continuous or discontinuous. It's the same thing. So there's nothing else to do here. That's it for this problem. Okay, so this time we want to check to see if it is continuous at c equals 0. This time we have a piecewise function, meaning this function is made up of 2 different equations. So for less than 0, the function is 2x plus 1, but for anything greater than 0, the function is 2x. So we're going to check all 3 conditions from the definition. So the first we want to check is f of c defined, meaning c is 0. So question is, what is f of 0? Well, according to the piecewise function, when x is 0, right here, we use this function. So you just plug it in. Let's plug it in. So 2 times 0 plus 1, that's going to be equal to 1. So f of 0 is 1. So that tells me that it is defined. Okay, so first condition is met. Now we have to do the second condition, where we have to check one-sided limits. We need to make sure that they are equal to each other. So let's get started checking that. So the first thing we want to do is check limit as x approaches 0 from the left. Now, we have two options, either 2x plus 1 or 2x. So what I want you guys to do, right, to make sure you know you're picking the correct one, think of the number line. We've done this before. Just think of the number line. The key point is 0. So from the left, that means you are moving to the right. You're coming from the left. That means you're moving this way. So what that tells me is that all these numbers coming from the left are less than 0. So that means that you have to use the first function. So from the left, we're going to use 2x plus 1. So now all we have to do here is plug it in. So 2 times 0 plus 1, that's going to be 1. So the limit as x approaches 0 from the left is equal to 1. Okay. So now we check limit as x approaches 0 from the right. Well, if you're approaching from the right, that means that all the x values are on this side, and all those x values are greater than 0. And if they're greater than 0, then that means that I will have to use the other equation, which is just 2x. So let's plug it in. 2 times 0, that's going to be 1. It's 0. So now the one-sided limits are different. And if the one-sided limits are different, that means that the limit as x approaches 0 of f of x does not exist. And if it does not exist, then that means that it is discontinuous there, or it doesn't satisfy the second property, this one. Remember, from the beginning, we said that these three conditions have to be met. The first one is f of c defined? So we say yes. The second one is that the limit of f of x as x approaches c exists, meaning one-sided limits are equal to each other. That condition is not met. So therefore, since it's not met, we say this. We say that f of x is discontinuous at c equals 1. So the question was, is it continuous? No, it's not. It's discontinuous. I'm sorry, it's not 1, it's 0. At 0. So it is discontinuous. Okay? Okay, here's another piecewise function. And this time we have three pieces. That's why it's called piecewise. It's made up of 3 pieces. This time we want to see, I want to check, is it continuous at c equals 1? So the first thing we need to do is check the first condition. Is f of c defined? Meaning, what is f of 1? Well, according to the function, the piecewise function, if x is less than 1, you use this equation. If x is greater than 1, you use this equation. But when x is equal to 1, the function is equal to 4. So therefore, f of 1 is 4. So the first condition is met. So now we're going to check the second condition, which was check one-sided limits. So the first one we want to check is what is the limit as x approaches 1 from the left of the function. Now we have to decide which of the 3 choices am I supposed to plug in. Well, from the left means less than 1. So therefore, less than 1 is 3x minus 1. So now we're going to check the limit as x approaches 1 from the left of 3x minus 1. Next step is easy, just plug it in. So it's 3 times 1 minus 1, and that will give me 2. Okay, so now let's check the limit as x approaches 1 from the right. From the right means greater than 1. And according to our piecewise function, greater than 1 means we're going to use 2x. So that's the function we're using. So that's going to be 2x. So now to find the limit, all you have to do is plug it in. So it's 2 times 1. 2 times 1 is 2. So now notice that the one-sided limits are equal to each other. What that tells me is that the limit as x approaches 1 of f of x, it exists. It's going to be 2 because the one-sided limits are the same. So now all I have to do is check the third condition, and the third condition was, does the limit as x approaches c of f of x, does it equal f of c? So now what I'll do is I'm going to replace the c with 1. So the limit as x approaches 1 of f of x, is it equal to f of 1? Let's see. F of 1 is 4. So this is going to be 4. And the one-sided limits are equal to each other, so the limit as x approaches 1 is 2. But we all know that 2 is not equal to 4. Since the last condition is not met, we say that f of x is discontinuous at c equals 1. And the reason is because the third condition is not met. The third condition, it is this one right here. So it's discontinuous. Okay, so for this problem, it's not asking us to see if it's continuous at a certain point. This one says, for the following problems, determine where each function f is discontinuous. Where is it discontinuous? So, first thing I want to do is check the domain. Now, this is a rational function. So that tells me that I have to look at the denominator. And in the denominator, we just have x. So to check the domain, you just say x, set it equal to 0. So that tells me that when x equals 0, we have 0 in the denominator, and we do not want that. So for the domain, we can say that it's all real numbers, but x cannot equal to 0. Because if it is, we have the function becomes undefined. And if that happens, that tells me that it is discontinuous. So this function is discontinuous at x equals 0. Notice the difference. Notice the difference. For the domain, we say x cannot equal to 0. Cannot. But if you want to check for discontinuity, we can say it is discontinuous at x equals 0, because there the denominator will be 0, and therefore it is undefined. 0 is not in the domain of the function, and therefore it fails the first condition. Okay, so this one is a little bit different. Now we have the product of two functions. So here we have square root of x times x cubed minus 5. And let's check the domain of both. That's what we need to do first. So if I look at square root of x, since square root of x is a radical, we know that whatever is inside the radical, it has to be greater than or equal to 0. So whatever is inside x in this situation, you set it to greater than or equal to 0. Guess what? That is your domain. x has to be greater than or equal to 0. So that we're done with that one. Now, for the next one, this one, I noticed that x cubed minus 5 is a polynomial. And for a polynomial, since it is a nice smooth curve, the domain is all real numbers. So what that means is that I can plug in any x value I want and I will get an answer. The problem with that is that if, let's say I decided to pick x equals -1, if I plug it in to x cubed minus 5, I will get an answer. But if I plug it into square root of x, square root of -1, that gives me an imaginary number. That cannot happen. So therefore, the question is, what numbers can I plug in? Well, this is the boss right here. That means you cannot plug in anything less than 0, because whatever x value you pick for x cubed minus 5, that's the exact same x value you have to plug into square root of x. So therefore, this function is continuous on x greater than or equal to 0. Nothing. Okay, let's look at this one. This one's a little bit different too, because not only is it a rational function, it also has a radical in the denominator. So let's see. Since we have a radical in the denominator, let's find when is it equal to 0. When is equal to 0? So when is square root of x minus 2 equal to 0? So let's solve for x. I would add 2, so the square root of x equals 2. Let's think about it. Square root of what gives you 2? 4. So that means that x has to equal 4. So when x equals 4, we cannot have, or better yet, we cannot have x equals 4 because the denominator will be 0. So therefore, x cannot equal to 4. So let me move this out of the way. That's one of the conditions. X cannot equal to 4. But also notice that we have a radical. So that tells me that inside the square root of x, right? Since we have the square root of x, we automatically know that x has to be greater than or equal to 0. So now, 4 is not in the domain. We cannot include it. But we need to know, when is it continuous? Well, to previous problem, we said that it was continuous from x greater than or equal to 0. But in this situation, if I just put x greater than or equal to 0, that means that the 4 has to be included there because it's 0, and then everything in between 0 and 1, and then everything in between 2, 3, 4, but 4 cannot be included. So therefore, we can say that it is continuous on, we can say x greater than or equal to 0, comma, but x cannot equal 4. Okay? So if you want to use a different notation or set notation, it would be something like this. X such that x is greater than or equal to 0, but x cannot equal 4. Same thing, just a fancy way of doing it. So there you go. Okay, so now it's going to get a little bit more difficult, but it's not that bad. Okay, so here we go. This time we have, not only do we have a radical where we know that everything inside has to be positive, but we also have a denominator. Okay, we have a denominator. So the first thing I would check is, when is the denominator equal to 0? So just set it equal to 0. So say x squared minus 1 equals 0. Now before you try and solve for x and add the 1. Don't do that because this looks to me like a difference of squares. So we're going to factor it. Now, we're going to factor it as x plus 1, x minus 1 equals to 0. And we check. When we solve, all you have to do really is take the opposite of the inside. So the opposite of x plus 1 is negative 1. Well, the opposite of 1. So x equals negative 1 and or x equals 1. At those 2 points, the denominator is 0. And therefore, that's what we do not want. Okay? So we do not want that. No, maybe I shouldn't do that there. Okay, so we do not want that. So let's see. Okay, so now another thing that we need to look for is we want to make sure that this radicand, the inside of the radical, is not negative. It needs to be positive. Now, one thing I noticed is that we have 4 in the numerator, and that's a positive 4. In order for us to get a negative inside the radical, the denominator, again, the denominator has to be negative because a positive 4 divided by a negative number will be negative. And therefore, we will have a negative inside the radical, and that's what we do not want. So what we want to do is find out when is x squared minus 1 greater than or equal to 0. Greater than or equal to 0 means positive. Well, it means equal to 0 positive. We don't want it to equal to 0. So let me get rid of that. So just when is it positive? When is it greater than 0? Okay, so this we've done before in class where you factor it. We already factored it previously. And we're going to do a sign analysis to figure out when is it equal to 0? Or better yet, when is it positive? When is it positive? So we put the critical points, the main points on the number line, which it's really these right here when it's equal to 0. So I will go put them in order, -1, and then +1. And if you remember correctly from when we were at class, you pick any point that is greater than 1, and then you plug it in here, see what you get when you multiply those two numbers. So if I pick something greater than 1, let's say a 2, if I plug it in here, we get a +3. If I plug it in here, we get a +1, and 3 times 1 is positive. So positive times positive is positive. So then we pick something between -1 and 1, and the easiest one will be 0. If I plug in a 0 here, we get +1. If I plug in a 0 here, we get -1, and a positive times a negative is negative. Now we pick something that is less than -1, -2. If I plug in a -2 here, we end up with a -1. If I plug in a -2 here, we end up with a -3. So negative times negative is positive. So now, this is what's happening. If I pick any number that is less than -1, we get a positive number. If I pick any number that is greater than 1, we get a positive number. If I pick anything between -1 and 1, we get a negative number. So those are the numbers that we do not want. So we want all the numbers that are less than -1 and greater than +1, because that will give me a positive number inside the radical. So basically that is our domain. Notice that x cannot equal, we said in the beginning, x cannot equal 1 or -1. We're not including it. Here, let me do this so you guys can see it. So I'm going to put an open circle there, and I'm not going to include it. We do not include those. So the domain for this function, domain is x such that x has to be less than, not equal to, because if it's equal, we get a 0 in the denominator, -1 union x greater than 1. So that is our domain. So what that means is that since that is our domain, that means that our function, right, f of x is not equal, is continuous on its domain, which is basically that. Okay, one more problem like this where we want to find where is it continuous, where is the function continuous. Now let's see. This one is a radical in disguise. Remember that if the exponent is a fraction or a rational exponent, then that tells me that it has a radical, the function. So in reality, if you want to rewrite this equation or this function, you can rewrite it as the square root of x plus 2. And we're going to find the domain because we want to figure out where is it continuous. And these functions are continuous on its domain. So let's find the domain. To find the domain, you want to get whatever is inside the radical, in this situation, x plus 2, and you set it to greater than or equal to 0. Now, then we solve. So if I solve for x, all I have to do is subtract. So x has to be greater than or equal to -2. So that basically is our domain. X has to be greater than or equal to -2. Now, therefore, if we think of the definition, it said that a function is continuous on its domain. So therefore, this function, so f of x, is continuous on here x such that x has to be greater than or equal to -2, and that one was much easier than the previous one. For the following problems, determine if the given function is continuous or discontinuous at the indicated point. Use the properties of limits. So basically, we want to check those three conditions from earlier. Are those three conditions met? And if they are, then it is continuous at those points, at the indicated points. So here we go. Let's see. Let's start with at x equals 4. So the first thing we need to check, is it defined at x equals 4? Meaning that's our C. So let's see. What is f of 4 equal to? So f of 4, before that, we need to look at these key points right here. Our key point, which is 6. So 4 is less than 6. So that means that I have to plug it into this function. So if I plug it in, 2 times 4 equals 8. Yes, it's defined. Now, second condition, does the limit exist? Does the limit exist? Meaning, we want to plug it in. We want to find out what is the limit as x equals 4. But for this one, think about it. Since this is a piecewise function, and we have different functions for at 6. So 4 is less than 6, so just plug it in. Let's see. So we say limit as x approaches 4. Well, that's going to be 2x, so you just plug it in again, and you get 8. So now the second condition is met, that the limit exists. So last condition is Does the limit as x approaches 4 of the function, is it equal to f of 4? Let's check. Well, f of 4 is 8, so this is 8. And the limit as x approaches 4 is also 8, so 8 equals 8, yes. So answer is yes, it is continuous at x equals 4. Continuous at x equals 4. So now we want to check, is it continuous at x equals 6? Let's see. So let's start off by changing colors. Okay, now at 6, is it defined? What is f of 6? If I look at the piecewise function, I'm going to use 2x if x is less than 6. But I'm going to use x minus 1 if x is greater than or equal to 6. It's equal to 6. So f of 6 means that I have to use the bottom function. So I plug it in. 6 minus 1, that's going to be 5. So yes, it's defined. Now we need to check the one-sided limits. Now you might ask yourself, why didn't you check the one-sided limits on the previous one? Because of this, because of the key point. At 6, we have, before 6 we have 2x, but after 6 we have x minus 1. That's why we need to check the one-sided limits there. On the other one we didn't have to. So here we go. So limit as x approaches 6 from the left. From the left means less than 6, just like I said on the previous questions. So less than 6 meaning we're going to use this function, 2x. So I just say 2x, plug it in. 2 times 6, that gives me 12. Now we need to check the limit as x approaches 6 from the right. From the right is our other function, which is just x minus 1. Now we're going to plug it in, so it's 6 minus 1, which gives me 5. So since the one-sided limits are different, then we say the limit as x approaches 6 of f of x does not exist. So therefore f of x is discontinuous at x equals 6. And the reason is because the limit does not exist at 6, because the one-sided limits are different. Okay, let's try another one, because practice makes perfect. So here we go again. We have a piecewise function. The key point is -2. And we want to check, is it continuous or discontinuous at x equals -2 and at x equals 10. So let's start with -2. First of all, let's check to see, is it defined at x equals -2? So question is, what is f of -2? Well, you have two options. When x is less than -2, you use this function. When x is greater than or equal to -2, you use this function. So -2, it's equal to -2, so I'm going to use this function, the bottom function, which is -2 plus 6. -2 plus 6 is 4. So it's defined. Now, since -2 is our point of interest, our key point, I need to check one-sided limits. So let's check the one-sided limits. So first, limit as x approaches -2 from the left. From the left means less than -2, so that means I'm going to use x squared. So next step, just plug it in. So I have a -2, make sure you use parentheses, squared, and negative 2 squared is 4. Please use parentheses, especially if you're going to use a calculator, which you don't really need for that problem. Now, next one, we want the limit as x approaches negative 2 from the right. From the right is just the other function, which is x plus 6. So I plug it in, plug in a negative 2. So negative 2 plus 6, and negative 2 plus 6 is equal to 4. Now, since the one-sided limits are equal to each other, we say limit as x approaches negative 2 of f of x equals to 4. So the limit exists. So our second condition is met. Now our third condition was, is the limit as x approaches negative 2 of f of x, is it equal to f of negative 2? And according to what we just did, f of negative 2 is 4, and then the limit as x approaches negative 2 is also 4. They're equal to each other. So we say this is going to be 4. This is also going to be 4. So yes, it is continuous at x equal negative 2. So now checking at 10, let's see, at 10, now 10, we're going to make things easy, or easier. At 10, that is greater than negative 2, because negative 2 is our point of interest. But 10 is greater than negative 2. So that tells me that the function that I need to use is x plus 6. Now, x plus 6 is considered to be a polynomial. It's a line, but it's still a polynomial. And since it's a polynomial, that is continuous everywhere when x is greater than or equal to negative 2. So therefore, 10 is greater than or equal to negative 2. So therefore, it is also continuous at x equals 10. That's the easy way. If not, you go ahead and do the 3 conditions to see if they're met. Okay, so now this one's going to be a little different, because now we are going to find the value of k so that f is continuous at negative 2. So here, instead of like the other problems where we were just finding where it's discontinuous, we want to find the value of k, this k here, so that it is continuous at negative 2. So what we want to do is we want to make sure that the limit as x approaches c of f of x is equal to f of c. In this situation, our c is negative 2. So what I'm going to do right now is replace c with negative 2. So limit as x approaches negative 2 of f of x equals f of negative 2. So I always like to work with the right hand side first. So I want to know what is f of negative 2. So I look for the equation or expression that has the equal. So it has to be this one. We're going to use 9 minus x squared if x is greater than or equal to negative 2. Equal to negative 2. So that means that on the right side, I'm going to get that equation, 9 minus x squared, but instead of x squared, I'm going to replace it with negative 2. Negative 2 squared. Make sure you put parentheses around it. And that tells me that on the other side, limit as x approaches negative 2, it's the other function, which is k over x squared. So k over x squared. So now all we have to do is evaluate. So let's plug it in. So we are going to plug in negative 2 into x. Okay? Again, because x is approaching -2. We plug it into x, not to k. So now we have limit as x approaches, no more limit since we are evaluating. That's my mistake. So it'll be k over -2 squared equals 2. And on the other side, this -2 squared is really a positive 4. So in reality, we have 9 minus 4. 9 minus 4 is 5. So let's keep on simplifying. So this is k over 4, because -2 squared is 4, equals 5. And the last thing we need to do is just to cross multiply. Imagine this one having a 1, so it doesn't really matter. K times 1 is just k. So that means that k is going to be 4 times 5, 20. So that value of k will make that function continuous at -2. So in order for you to be able to do these problems, you need to know your algebra. Okay? Algebra. Here we go. Let's do another one. For the following function f, find the value of k. Find the value of k so that f is continuous at 2. So we're going to do the same thing again. We're going to set it up as, let's see, limit as x approaches c of f of x, is it equal to f of c? In this situation, our c equals 2. So let's plug it in now. So limit as x approaches 2 of f of x equals f of 2. Now, we need to decide which function am I going to use for f of 2. You have to look for the one that has the equal sign. So this one has the equal sign. So that means that on the right hand side, we're going to use this function. And wherever you see an x, you're going to plug in a 2. So like this. So it'll be 2 squared minus 5 times 2 plus 3. Notice that all I did was I replaced the x's with 2. On the left hand side, we have to evaluate the limit. So it's going to be the limit as x approaches 2. Well, obviously it has to be the other function, which is just kx plus 1. So now let's evaluate. When we evaluate a limit, just plug in. Notice that x is approaching 2. So x is approaching 2. So replace the x with 2. The x, not the k. So now it would look like this. K times 2 plus 1 equals. Now we have to simplify. So this gives me 4 minus 10 plus 3. K times 2 is just 2k plus 1 equals 4 minus 10 plus 3 is negative, negative 3. So then all we have to do is solve for k. To solve for k, I need to subtract 1. So 2k equals negative 3 minus 1 is negative 4. Divide by 2, k equals negative 2. We're done. So basically, to know how to find k, you need to know that you have to use this definition and then just solve for k and know your algebra, of course. Okay, let's try one more just to make sure that you're understanding. So again, we want to find the value of k so that f is continuous at 3. So again, k, and we want to see what value k will make f continuous at 3. So again, I want to start off by writing the definition of continuity. So keep writing it. limit as x approaches c of f of x, is it equal to f of c, or when is it equal to f of c? In this situation, c is 3. So now we replace the c with 3. So limit as x approaches 3 of f of x equals to f of 3. Now if we look at our functions, I always look for the right function first. This one, f of 3, meaning which one am I going to pick? What is the y value, or the value of f when x equals 3? Well, when x equals 3, we just have k. That's perfect, easy. So that means that on the right hand side, f of 3 is just k. So that means I have to take the limit as x approaches 3 of the other function, which is x squared minus 9 over x minus 3. Now, when we evaluate a limit, all you have to do again is plug it in. But in this situation, if I plug in a 3 to that x, we get 9. 9 minus 9 is 0, so we have 0 on top. And if I plug in a 3 into that x, we get 0 in the denominator. So we have 0 over 0, an indeterminate form, which we do not want. And when that happens, we have to somehow simplify it to cancel something. So we're going to rewrite it. I notice that the numerator, x squared minus 9, is a difference of 2 squares, so I can factor it. So it'll be limit as x approaches 3. X squared minus 9 can be factored as x plus 3, x minus 3 over x minus 3 equals k. So now I notice that I can cancel the x minus 3's. So that means that I'm left with, let me go this way. I'm left with limit as x approaches 3 of just x plus 3 equals k. And now we can just simply evaluate it. So I will plug in a 3 wherever I see an x, meaning this 3 gets plugged in there. That equals k. And notice that once I plug in the x, the limit sign is no longer there. You don't need it anymore once you plug in. So here, 3 plus 3 is 6. That equals k, and we are done. Okay, the last thing I want to talk about today is this theorem called the intermediate value theorem. So I'll read it, and then I'll explain what we use it for. So let f be a function that is continuous on a closed interval, a to b, and f of a is not equal to f of b. If n is any number between f of a and f of b, then there is at least one number c in the open interval, a to b, for which f of c equals to n. So the best thing to do with this is that we can use it. We can use the IVT, the intermediate value theorem, to locate zeros of a function. So suppose that a function f is continuous on a closed interval a to b, and f of a and f of b have opposite signs. Again, opposite signs, meaning one is positive, one is negative. Then by the intermediate value theorem, there exists at least one number c between a and b for which f of c equals to 0. That is, f has at least one 0 between a and b. So we're looking for zeros. It's not going to tell us how to find it, but it's not going to tell us what the c value is, but we know that there is at least one c value in that interval that'll give us a 0 for the function. So this is really an existence theorem. So let me explain. So for example, it says use the IVT to determine which of the functions must have zeros in the given interval. So for this one, we're going to need a calculator. Let's see. So now what we want to do is just evaluate f of a and f of b. So meaning this is your A, this is your B. So let's see. F of negative 3. What is f of negative 3? F of negative 3 is going to be 25 minus 8, and then negative 3 squared minus negative 3 cubed. And for this one, if we use a calculator, and make sure that if you use a calculator, plug it in exactly how you see it. Exactly how you see it there, just like I've taught you before. So 25 minus 8 parentheses negative 3 squared minus a negative 3 cubed. That's going to give me negative 20. So that means that f of negative 3 equals negative 20. So now we're going to find what is f of b, meaning what is f of 0. So now I will plug in a 0. So 25 minus 8, 0 squared minus 0 cubed. But when we plug in a 0, it's easy. It's gone, so we're just left with 25. Now notice that f of 0 is 25. So what's happening here is this. Since f of negative 3 is negative 20, and f of 0 is positive 25, we can say this. Because f of negative 3 and f of 0 have opposite signs, by the intermediate value theorem, there is a C such that f of C equals to 0. So there, we just proved that since f of negative 3, or f of A, and f of B, f of 0, have opposite signs, there has to be a value between negative 3 and 0 such that when you plug it in, you get a 0. And that's basically it. It's just an existence theorem, and that helps with other applications which we'll do later on. Okay, let's do another one. So again, this is your A, this is your B. Let's find out what is f of A, or better yet, what is f of 0. So that tells me just plug it in. So it'll be 0 squared minus 4 natural log of 5 times 0 plus 2. Let's simplify. So that's going to be negative 4, because 0 squared is gone. Natural log of 2. So we get our calculator, and we find out what is negative 4 times natural log of 2. And that gives me a negative number. So I'm going to write it as f of 0 equals, and since it's giving me decimals, I'm going to round to 3 decimal places, which is negative 2.773. So there. Now we want to evaluate what is f of b, meaning what is f of 4. So let's plug it in. So it'll be 4 squared minus 4 natural log 5 times 4 plus 2. So this will give me 16 minus 4 natural log. Inside the the natural log, we have 5 times 4, which is 20, plus 2 is 22. Now we plug it into our calculator, and we get, let's see, 16 minus 4 natural log of 22, and we get that f of 4 is 3.636. Now notice, f of 0 is negative, f of 4 is positive. That tells me that by the intermediate value theorem, there's going to be a c in the interval from 0 to 4 that's equal to 0. So we're going to write it like this. Since f of 0 and f of 4 have opposite signs, the IVT states, I'm going to write it a little bit different, states that f of c equals to 0 for at least one number c in the interval. The interval has to be the open interval, so in the interval from 0 to 4. That's it. And yes, you do have to write all that out. Okay, promise you this is our last problem. So again, we want to find, we want to see if there's any zeros in the given interval by using the intermediate value theorem. So here we go. Again, this is A, this is B. Let's find out what is f of 10. So we replace all the x's with 10, so it'll be 10 over 10 plus 1 squared, which is really, let me erase this, 10 over 11 squared. And if we use a calculator, right, 10 divided by 121 gives me a positive 0.083. So there. Now we need to find what is f of 20. Plug in a 20, so we have 20 over 20 plus 1 squared, which is just 20 over 21 squared. Now, even though we don't, if you can see that the answer is going to be positive because we're squaring the denominator, we have no negatives, so still want to figure out what the number is. So 20 divided by 21 squared, that gives me 0.045. So that is f of 20. Now notice that when I plugged in the 10, we got a positive number. And when I plugged in 20, we got a positive number. So this time, since they don't have opposite signs, we have no idea if there is a 0 in the interval from 10 to, or if there's a c that'll give me 0 for the function in the interval from 10 to 20. So since we don't know, then we just say that the IVT gives no information. So we don't know. We do not know if there is a value of c that when I plug it in, it'll give me 0 in that interval. And that's it for that one. Please do all the problems. I know that there's a lot, but please do them.